Hello, we're going to talk about the proof of Euler's formula. And Euler's formula is this. It's EI to the theta. That's the complex number I. And then it's is equal to cosine theta plus I sine theta. So this is a proof that I found that can help you with it. But this video, I'm going to make this optional. If you don't want to watch this, you just want to take it that this is true and use it, that's great. But if you want to see why, here we go. There is one proof that we can do that has some of the knowledge that we know, but we're gonna have to consider this I as this complex number I as a constant, just like this. And the way that we're gonna do this is we're gonna let this we're gonna come up with this function. We're gonna use this function f of theta is equal to e negative I theta times the cosine theta plus I sine theta. Good. And then we're going to differentiate this, right? So I'm going to say f prime of theta, the first derivative, and this is a product rule. So if I take the derivative of this guy, it's going to be negative I e negative I theta, right? Times this guy, which is cosine theta plus I sine theta, right? And then now the product rule, I'm going to take the derivative of this times this guy, so it's a negative I theta. That's not going to change, but this guy will. The derivative of cosine is the negative sine theta plus I cosine theta, because the derivative of the sine is just the cosine. And now I can factor out, you can see in both these expressions, right? E negative I theta, and then what am I going to be? And here I got this negative I sine, this negative I, and I'll have a negative I cosine theta. Now this would be I times I is a negative, that would be I squared, which is negative 1, so that's going to be plus sine theta, right? Now on this side, it just stays the same. It's going to be negative sine theta. I can just make this minus sine theta, right? And plus I cosine theta. Now look what happens inside of here, right? So if I look what's going on, right? Negative I cosine theta, I cosine theta, those cancel out, right? Gone. And then these guys cancel out. So what does this end up being? This ends up being 0. So this is equal to 0. F prime of theta is equal to 0. What does this imply? This implies that that the derivative is 0, right? There, that means that the whole function f of theta is some constant number k, right? So it's some constant number, right? So for the whole function, no matter what, right? So we're going to figure out what that theta is. So I know if f of theta is equal to k, right? Then I know that e to the negative I theta times cosine theta, cosine theta plus I sine theta is equal to k. And I can figure out what that k is, what this actual constant is, by, I'm going to plug in, let's say theta is equal to 0, right? If theta is equal to 0, what do I get? This becomes just 1, right? So I get 1. Cosine at theta is negative 1, right? But I'm sorry, cosine at 0 degrees, my bad, at 0 degrees is just positive 1, but the sine is just 0, right? Equals k, so my k is just equal to 1. So what does that mean, right? That means that f of theta, this guy right here, e to the negative I theta times the cosine of theta plus I sine of theta, that's just equal to 1, right? And then I can multiply both sides by e I theta, positive 1, and then I'm going to get cosine of theta plus I sine theta, and that's going to be the e I theta, right? And that is what we wanted to show, right? this guy right here is the Eulers form their identity, right? So that's what we wanted to show up here. Good. Now there's a special case that we need to go over too. That's important. What about if theta is equal to pi, right? Well, if I plug theta into pi, I get -1, right? Plus theta into here, it's just 0, right? Is equal to ei to the pi, right? And this is what's referred to as Euler's constant, or I can add 1 to both sides, and ei to the pi equals 1. And this is kind of, if you think about it, what do you have here? We got an exponential number, right? It's an irrational number. It goes on forever. We got 2, basically. We got the exponential 2.7, and it keeps going on forever, pi. And then we have a complex number, and it comes out to just evenly 1. So it's, you know, it's sometimes called the most beautiful equation in math. But it is kind of an interesting concept, and we showed it just right here. Sound good, guys? Thanks.